There's this incredible piece of tech that's kind of quietly powering our world, totally behind the scenes. Well, today, we're going to pull back that curtain and take a look at the DC machine.
So think about this for a second. What on earth could an electric train, a massive industrial crane, and your kitchen blender possibly have in common, right? I mean, one is all about immense power, and the other, not so much. But you'd be surprised to learn that the very same fundamental principle is at the heart of all of them.
And that's where this single, elegant device comes in. It's something that can turn electricity into motion and then, get this, turn motion back into electricity. We're talking about the DC machine, and it is a true marvel of engineering. So let's dive in and figure out how it pulls off this incredible trick.
All right, Section 1, the reversible energy machine. So what is this thing? How can one single device work in two completely opposite ways? I mean, how can it be both a motor and a generator? Let's find out.
Well, at its core, a DC machine is an electromechanical device. That just means it converts energy between mechanical and electrical forms using direct current. The best way to think about it is like a two-way street for energy. And what's really cool is that its whole identity, whether it's a motor or a generator, is all down to which way that energy is flowing.
Okay, Section 2, motor versus generator. This incredible duality gives the DC machine two totally different personalities. So let's get to know both of them, the motor and the generator.
Now, if you put a DC motor and a DC generator side by side, they'd look pretty much identical. But what they do is a perfect mirror image of each other. It really all boils down to one simple thing. Which way is the energy going? So let's break that down.
First up, the DC motor. This is the one you're probably most familiar with, even if you don't realize it. Think of it as a consumer of electricity. You feed it electrical energy, specifically direct current, and what do you get out? Mechanical energy. That's right, rotational motion that can do real work, like spinning a fan or lifting an elevator.
Then on the complete flip side, you've got the DC generator. This one's a producer of electricity. You give it mechanical energy, you spin its shaft with an engine or a turbine or something, and out comes electrical energy in the form of DC power. It's the exact opposite process. All right, Section 3 is the anatomy of a DC machine. So the big question is, how on earth can one device do both of those things? Well, to figure that out, we've got to pop the hood and look inside. The secret is all in how it's built. So every single DC machine, it doesn't matter if it's a motor or a generator, is built around two main parts. You've got the stationary part, called the stator, and the part that rotates, the rotor. Let's start with the outer frame, the machine's skeleton, if you will. That's the stator. So the stator doesn't move. Its whole job is to set up a powerful stationary magnetic field, basically creating the stage for all the action. You've got the yoke, which is the frame holding it all together. Then you have the field poles, which are essentially electromagnets, and the field windings, which are the coils that power them up. And don't forget the brushes. Those little guys are super important. They're the critical link that gets the power to the spinning parts. Okay, now for the star of the show, the part that actually moves. Spinning right inside that magnetic field is the rotor, and it's really the heart of the machine. It's got the armature core and, wrapped around it, the armature winding. These are the copper conductors that are going to do all the heavy lifting. But see that last part on the list? The commutator? Oh man, you're about to see why that little piece is the absolute genius of this whole design. Okay, Section 4, the magic of commutation. Now we get to the really clever bit. The secret sauce that lets a DC motor spin continuously in one direction instead of just, twitching back and forth like a confused robot. This is the magic of commutation. So here's the problem you run into with basic physics. When you run current through a loop of wire, that's our armature, and put it in a magnetic field, it gets a push. It starts to turn. Great. But as soon as it spins halfway around, that same force starts pushing it back the other way. So you just get this rocking motion, back and forth, back and forth. So how do you fix that? How do you get a smooth, continuous spin in just one direction? And this is where that brilliant mechanical solution comes in. Let's walk through it step by step. First, current goes through the armature. The magnetic field does its thing and creates a force that makes it turn. So far, so good, but right as it spins past that halfway point, that force is about to flip and start pushing it backwards. This is the magic moment. Just as that's about to happen, the brushes hit a little gap on that spinning switch, the commutator. This instantly reverses the direction of the current flowing in the armature, and because the current is now flipped, the magnetic force gives it another push in the same direction as before.
It's such a clever, purely mechanical solution to a physics problem.
So let's zero in on that key component, the commutator. You can honestly think of it as the machine's mechanical brain. It's this segmented ring, a rotating electrical switch, that spins right along with the armature. And at the exact right moment, just before the magnetic force would reverse, the brushes make contact with the opposite segments. This simple action flips the direction of the current in the armature. And that ingenious flip means the torque, the turning force, is always pushing the rotor in the same direction. That's how you get that smooth, non-stop rotation.
Okay, Section 5, DC machines in action. So now that we've got the how figured out, let's connect it all back to the real world. Where do these things actually shine?
This is what's so cool about them. Just by changing how you wire up the field and armature windings, you get totally different behaviors. You can have a series motor, which gives you a massive amount of torque right from a standstill, perfect for getting a heavy train or crane moving. Or you could have a shunt motor, which is all about constant speed, great for things like fans or machine tools. And then there are compound motors, which kind of give you the best of both worlds, which is why they're great for stuff like elevators.
So what can we take away from this? I mean, in our super digital age of complex electronics and sophisticated software, what can we really learn from this marvel of 19th century ingenuity? I think it's a powerful reminder, right? It shows us that sometimes the most elegant, the most robust, and the most timeless solutions aren't the most complicated. They're the ones built on fundamental principles of physics, engineered with a kind of brilliant, beautiful simplicity.